Hey, curious minds, and welcome. I'm NerdTeach. Today, we're going to pull back the curtain and take a peek right into the heart of your computer. We're about to uncover a secret that will literally change the way you see numbers. You ready to have your mind blown? Let's get into it.
So get this. What if I told you that for a computer, the number -1 looks like the biggest, most maxed out number it can possibly imagine? I know, it sounds totally backward, right? Like saying left is the new right. But here's the thing. It's not only true, it's one of the most brilliant tricks in all of computer science.
Just look at this. A string of 8 ones. All the lights are on. To a computer, this means -1. I know, it looks like a glitch in the Matrix, doesn't it? But trust me, by the end of our little journey today, you'll see this isn't a bug, it's a feature of pure genius. And I can't wait to show you how it works.
To really get this magic trick, we have to start at the very, very beginning. I want you to imagine a super simple world. A world where our computer can only count things it can physically see. A world without debt, a world without freezing temperatures, a world without any negative numbers at all. You see, the tiniest, most fundamental piece of info in any computer is something called a bit. And the absolute best way to think of a bit is just a simple light switch. It's either off, which the computer calls a 0, or it's on, which it calls a 1. That's it. That's the whole foundation right there. Pretty simple, right?
And to build numbers, computers just line up a bunch of these switches. A super common setup is a row of 8 of them. We call that an 8-bit number. So just picture a little team of 8 light switches, and by flipping them on and off in different patterns, we can create all sorts of numbers. It's like their own little secret code.
Now, the most basic way to count with these switches is called an unsigned integer. It's a fancy name, but all it means is we're only counting positive numbers. Every switch you flip on adds more value to the total. All switches off, that's 0. All switches on, that's the biggest number you can make, 255. It's a happy, positive-only world for now.
But you know, the real world isn't always so simple and sunny. We've got things like debt, we've got freezing temperatures. We need to be able to go backwards. So the brilliant engineers back in the day had a huge puzzle on their hands. How in the world do you teach a simple row of light switches about the idea of a negative number?
And so this fascinating quest began. I mean, these brilliant minds needed to invent a system, a set of rules for these switches that was simple, that made sense, and crucially, didn't need a bunch of complicated new hardware. Their first idea? Well, it's probably exactly what you'd think of first.
They called it sign magnitude. And the idea was super intuitive. They said, hey, let's just take that very first switch, the one all the way on the left, and make it a special sign switch. If it's off, a 0, the number's positive. If it's on, a 1, the number's negative. The other 7 switches, they just represent the value, the magnitude.
It's so clean, right? To get +5, the sign switch is 0. You want to get -5, you just flip that one switch to a 1. The rest of the pattern is identical. It's elegant, it's easy to read, problem solved, right?
I mean, it seems perfect, but this is one of those classic moments in programming. You think you found this amazing, simple solution, but then you spot this one tiny hidden flaw that just messes up the whole thing. Have you ever felt that when you're coding? That moment where you just stare at your screen and go, wait a minute, that can't be right.
Well, they hit that exact moment. And the flaw they discovered was so weird and so fundamental that it sent them straight back to the drawing board. It was the problem of having 2 different ways to write the number 0.
Okay, check this out because this is where it gets weird. With sign magnitude, having all the switches off gave you +0. That makes sense. But what about when the sign switch is on and all the others are off? Well, that gave you -0. What does that even mean? Another early attempt called 1's complement had the same exact problem, just with a different pattern. This was a total nightmare for the hardware. How can a computer check if something is 0 if there are 2 different versions of 0? It's just confusing. And hey, let me just pause and say this. If this part feels a little confusing, that is 100% normal. I remember when I first learned this stuff, my brain did a complete somersault. This is one of those tricky spots that really makes you think. So if you're with me, you're doing awesome. Stick with it.
So out of that mess of having 2 different zeros, a hero emerged. A system so elegant, so clever, and so efficient that it's used in basically every single computer, phone, and smart fridge on the planet today. Its name is 2's complement.
Okay, so here it is. Here's the breakthrough, the big idea. What if we stopped thinking of that first switch as just a simple sign? What if instead, when that first switch is on, it doesn't just mean this is a negative number, it actively subtracts a huge value from the total? In our 8 switch example, it's like putting a weight of -128 on the scale. Whoa, right?
This wild idea leads to this beautiful, almost magical recipe to find any negative number. First, you start with the positive version you want. Let's say +1. Next, you invert every single bit. Flip all the 0s to 1s and all the 1s to 0s. And for the last step, you just add 1. And poof, you get the perfect negative representation. So for -1, we take 1, we flip it to get 1, 1, 1, 1, 1, 1, 0, we add 1, and we get all 1s, the biggest possible pattern.
And this isn't just theory. You can cast this spell yourself in a real programming language. Look, right here in C++, we're creating an 8-bit signed number and giving it the pattern of all 1s. Then we ask the computer, hey, what number is this? And it doesn't say 255. It tells us it's -1. It actually works. And it's the exact same story in another language, like Java. The words are a little different, but the computer's deep down logic is the same. That binary pattern of all 1s is universally understood by modern machines as -1. This is the language they all secretly speak. So this is way more than just a cool party trick. 2's complement completely changed the game for how computers do math. But why? Why was this the idea that won out and became the standard for the entire world? Well, it boils down to 3 huge game-changing advantages. First, and this is the big one, it solved the 2 zeros problem. Now there's one and only one way to write 0, all switches off. Boom, confusion gone. Second, and this is incredible for efficiency, the circuits for adding and subtracting numbers could now be the exact same piece of hardware. This made computer chips way simpler, cheaper, and faster. And as a cool little bonus, this system gives us one extra negative number we can use. It's a total win-win-win.
This table right here, this brings it all home. It shows you the 2 different worlds living side by side. Just look at that last row. In the simple, positive-only world, all ones means 255. But in our new, clever, signed world, that exact same pattern of switches means -1. And check out the middle row. The pattern that used to be 128 now becomes -128. The number line wraps around. This is the secret life of numbers, and now you're in on it.
You know, I really want you to remember this. You don't have to be some kind of super genius to learn how to code. You just need these little moments of clarity, these aha moments. And today, you've had one. You've really understood a deep, fundamental piece of how computers work. That's a huge deal. You should be proud of that.
So I'm going to leave you with this final thought. The next time you're coding and you get a bug and some gigantic, random-looking number pops up on your screen, take a breath, don't panic. Just ask yourself, wait a second, could that giant number just be our old friend -1 wearing a really clever disguise? Thanks.
Hey everyone, Nerd Teach here. Come on in, I'm about to let you in on a little secret. It's a kind of magic, really. A secret power that every great programmer eventually discovers. So here's the thing. Computers, they don't actually understand the code we write. Not really. Deep down, they're speaking a totally different language, a hidden language of just ones and zeros. And if you learn how to speak that language directly, oh, it's like finding a cheat code for reality. You can make your programs ridiculously fast. So today, we're going to crack open the spellbook and learn about bitwise operations. All right, so every good sorcerer needs a toolbox, right? Some essential gear. For our kind of bit magic, our tools are called operators. You can think of them as the basic words of power, the fundamental spells that let us mess with the very fabric of data itself. So let's pop this thing open and see what's inside.
Yeah, these operators are literally our magic words. See, instead of politely asking the computer, hey, would you mind checking if this number is odd, we can just speak its language directly and say, yo, is your last bit a 1? It's the difference between asking a stranger for directions versus knowing the secret alleyway that gets you there in half the time.
Okay, first tool out of the box is the AND operator. And I want you to think of this one as a stencil, like a magical stencil. Its whole job is to mask things out, to let us zero in on exactly the bits we care about. It's all about precision.
Next up, we've got the OR operator. If AND was a stencil, then OR is our magic glue. Seriously, its job is to combine things, to stick different bits together to build something new. Think of it as adding powers or turning on features.
And finally, the weird one, the most clever, most mysterious tool we have, the XOR operator. The best way to picture this one is like a light switch, a little toggle switch. It doesn't add or remove, it just flips. And trust me, this little guy has some seriously cool tricks up its sleeve.
All right, let's grab our first tool and actually use it. Time to see how this AND stencil really works. So, the AND operator is, well, it's really strict. Think of it like a bouncer at a super exclusive club. To get a 1 out of it, the bit from A and the bit from B both have to be a 1. If even one of them is a 0, nope, you're not getting in. The result is 0.
And this is exactly why that stencil metaphor is so perfect. Imagine you've got this pattern, and you lay a stencil over it. The light only shines through where there's a hole in both the pattern and the stencil, right? It's the same deal here. A 1 only makes it through if our number has a 1 and our mask has a 1 in the same spot. So what could we use that for?
Okay, check this out. This is where the magic gets real. How do you know if a number is odd? In binary, it's super simple. You just look at the very last bit. If that last bit is a 1, the number is odd. That's it. So what if we make a mask that's all zeros except for a 1 at the very end, which is just the number 1? When we AND our number with that mask, what happens? Everything else gets zeroed out and we're left with only the last bit. If the result is 1, boom, the number was odd. This is so much faster than telling the computer to do division. It's like one single thought for the processor.
Awesome. One tool down. Now let's switch gears from filtering things out to building things up. Let's grab our magic glue, the OR operator.
Now compared to that strict bouncer AND, the OR operator is way more chill. It's more like a party host. It gives you a 1 if bit A is a 1, or if bit B is a 1. Or heck, if they're both 1s. The only way you're getting a 0 is if everybody brings a 0 to the party. It's all about bringing things together.
And that's why we call it magic glue. The main thing to remember is this. You use OR when you want to force a bit to be on. No matter what a bit's value is, if you OR it with a 1, the result will always be 1, guaranteed. This is perfect for like turning on settings or adding permissions. Here's a classic example you see all the time in operating systems. Imagine the read permission for a file is the binary number 100, and the write permission is 010. Okay, so what if you want a file to have both permissions? You just OR them together. You get 110. That single number now holds both pieces of information.
We literally just glued their powers together.
Okay, deep breath. Now for the weirdest and maybe the coolest tool in our toolbox. The one that doesn't just check or set, it flips. Get ready for the strange and wonderful magic of the XOR switch.
XOR stands for exclusive OR, and its whole personality is right there in the name. It's exclusive. It only likes it when things are different. Look at the table. You only get a 1 out if the inputs are different from each other. 0 and 1, you get a 1. 1 and 0, you get a 1. But if they're the same, 0 and 0, or 1 and 1, nope, you get a 0.
So because it's a difference detector, it has this amazing side effect. It's a perfect toggle switch. Think about it. If you XOR any bit with a 0, nothing changes, right? Because they're not different, its value stays the same. But if you XOR a bit with a 1, it flips. A 1 becomes a 0, and a 0 becomes a 1. It's a perfect targeted light switch for any single bit you want.
And here's how you actually write the spell in languages like C++ or Java. That 1KK part, that's another bit of magic called a bit shift. All it does is take the number 1 and just slide it k spots to the left. This creates a mask with a single 1 in exactly the position you want to flip. So when you XOR your number with that mask, only that one target bit gets toggled. Everything else, totally untouched. It's just so clever.
Okay, so we've learned the basic words of power. Now it's time to put them together and cast some real spells. These next couple of tricks are absolute classics, and they show you just how powerful this stuff can be.
You gotta see this. This is a super famous problem you see in coding interviews all the time. How do you swap the values of two variables, A and B, without creating a third one to hold the value temporarily? The answer is XOR. I know, these 3 lines look like complete gibberish, but they work. It's this beautiful, mind-bending little dance where the numbers trade information back and forth until they've switched places. No extra memory needed. Wild, right? Here's another brilliant one. You know how computers store letters, right? Using a system called ASCII? Well, it turns out the only difference between a capital A and a lowercase a is a single bit. Just 1. And guess what number is all zeros except for a 1 in that exact spot? The number 32. So if you XOR any letter with 32, you just flip that 1 bit and you instantly switch its case. No if-then statements, no complicated logic, just one tiny, super fast operation.
Okay, let's do a super quick recap of our new magical tools. Remember, AND is the stencil you use to mask and isolate bits. OR is the glue you use to set and combine bits. And XOR is the clever little switch you use to toggle and flip bits.
And look, I just want to leave you with this. If your brain feels a little bit fuzzy right now, that's a good thing. It's totally normal. It means you're stretching it and learning something new. You don't have to be a genius to get this stuff. You just need clarity. I promise you, every single great programmer you look up to once stared at these exact same symbols and felt completely lost. You just took a massive step toward understanding how computers actually—
Hey there, curious minds. I'm NerdTeach. Welcome. Today, we're going to pull back the curtain on a little piece of programming that feels, well, it feels a lot like magic.
Now seriously, just think about it. What if you had a single line of code that could solve really tricky problems with just, like, unbelievable speed and grace? It sounds like something from a fantasy novel, right? But in the world of programming, this is 100% real.
And this right here is our spell. I know, it looks a little weird, a little cryptic, doesn't it? This little expression, it's kind of like a secret handshake used by expert programmers. It's this super powerful trick that unlocks some incredible efficiencies. And today, you and we're going to decode it together.
Okay, so let's peek inside the magic box. To really get this trick, we first need to learn the computer's secret language. But don't worry, you're not going to need a calculator or anything, just a little bit of imagination.
You see, every number has a secret identity called binary. The easiest way to picture it is to just imagine a long string of light bulbs. An on bulb is a 1, and an off bulb is a 0. So when we see the number 12, the computer just sees this pattern of lights: on, off, off. Pretty simple, right?
Now for the first part of our spell, subtracting 1. Think about what happens when you subtract 1 from, say, 100. You can't take 1 from 0, so you have to borrow from the left and it becomes 99. Well, binary works the exact same way. When we subtract 1 from our 12, which is 1100, we have to borrow. And this kicks off a really cool chain reaction. The rightmost on light, it turns off, and every single off light to its right flips on.
And now for the final piece of the puzzle, the AND operator. That's what that little ampersand symbol is. Just imagine it as a filter. We lay our 2 light patterns on top of each other, and a light in our final result stays on only if it was on in both of the patterns above it. And look what happens. That whole chain reaction on the right, it just gets filtered out, and one specific light gets turned off. And that's it. That's the secret. This little trick, n and n-1, is what I like to call a magic bit eraser. Its one and only job is to find the rightmost on light in any number's pattern and, poof, turn it off. That's the whole technique. So now that we know how it works, let's see what we can do with it.
All right, we have our magic eraser. So let's put it to the test with our very first puzzle. I call it the lone light. So how can we quickly tell if a number is a power of 2? You know, like 2, 4, 8, or 16.
So using our glowing lights metaphor, a power of 2 is just a number with a single light bulb turned on. The number 8 is 1000. The number 16 is 10000. See? Just one lone light. So how can our magic eraser help us spot this? What do you think happens next? And here is the absolutely beautiful solution. If a number has only one light on, like 16, and we use our magic eraser on it, what happens? Well, the eraser turns off that single light, and we're left with 0, nothing. But if a number has more than one light on, like 12, erasing 1 still leaves other lights behind. Have you ever felt this while coding, where one simple little trick just perfectly solves what seemed like a really big problem?
And here it is, the spell written out, straight from a programmer's spellbook. In both C++ and Java, it's the same logic. We just check if the number is positive, and if using our magic eraser on it gives us 0. It's clean, it's super fast, and it's just so elegant.
Okay, that was really cool. But what if we want to count all the lights that are on, not just check if there's only one?
So this problem is called bit counting, or sometimes population count, and it comes up all the time in things like data compression and cryptography. Now the slow way would be to check every single light bulb one by one, but we have a magic eraser, so can we do better?
Of course we can. Instead of checking every single position, we can just use our magic eraser again and again. See, each time we use it, we know we've turned off exactly one light, so we just keep a counter. For the number 12, we erase one light, our count is 1. We erase the next one, our count is 2, and now all the lights are off, so we stop.
The final answer is 2. And what's so brilliant about this is that the code only loops as many times as there are on lights. For a number that might have only 2 lights on out of, say, 32 possible positions, we only loop 2 times, not 32 times. It is incredibly efficient. And this is how that logic looks as a spell. It's famously known as Bruijn Kernighan's algorithm, and it is a true classic. Seriously, if you ever go for a programming interview, there's a really good chance you'll see this one. It's just a beautiful example of thinking smarter, not harder. All right, for our final puzzle, let's level up a bit. What if we need to find what a whole range of numbers, say from 9 all the way up to 12, what do they all have in common at the binary level?
This problem is called the range bitwise AND. We want to find the pattern of lights that stays on for every single number in a given range. Now, the obvious way would be to AND every number together one by one, but that could be incredibly slow if the range is huge. We need a bit of magic.
So here's the deep insight. Within any range of numbers, the lights on the right side, they're going to flicker on and off constantly. And any light that flickers, even just once, is going to be turned off when we AND everything together. The only lights that survive are the ones on the left, the ones that stay the same for the entire range. So how do we find them? Well, our magic eraser gives us a shortcut. By repeatedly erasing the rightmost on light from the bigger number, we're basically trimming away that flickering part until it shares the same stable, common prefix with the smaller number. And the code for this is just, it's stunningly simple. I mean, look at that. We just keep shrinking the larger number with our eraser until it's not bigger than the smaller number anymore. Whatever's left, that's the shared pattern. We've solved a potentially massive problem with a tiny, elegant loop. It's awesome. So let's just take a breath for a second and recap the incredible power we've just unlocked with this one simple trick.
From just a single building block, our magic bit eraser, we've built a whole toolkit. We can check for lone lights, we can count all the lights super efficiently, and we can even find the common core of a whole range of numbers. This right here is the beauty of computer science. Simple, elegant ideas that create really powerful solutions.
And I really want to leave you with this thought. If any of this felt tricky at first, that is completely normal. Every single great programmer once felt confused by these exact same ideas. The goal isn't to be a genius, it's just to see clarity, one concept at a time. And you're doing that right now. Hey everyone, I'm Nerd Teach. So glad you're here. Today, we're going to do something a little different. We're closing the textbooks and opening up a spell book. Yep, you heard me. We're about to learn the secret, ancient language of computers, the powerful magic of bit manipulation.
What if you could literally bend the fabric of data to your will, using nothing but zeros and ones? Sound impossible? Well, stick around. You're about to become a binary sorcerer. Let's do this.
So welcome, apprentice. I'll be your guide. And today, we're learning 3 incredible spells. First, we'll learn a spell that can conjure up every single possible combination of things. Then, we're going to build a magical ladder for some seriously lightning-fast counting. And for the grand finale, we'll learn an illusion, a spell to hide secret messages right inside a picture in plain sight.
Okay, let's open the book to chapter 1. This is our first lesson, and trust me, it's a fundamental spell that can solve a huge range of problems you're going to see out there. And to keep things simple, let's talk about something we can all agree on. Pizza, right? Okay, imagine you've got toppings, say pepperoni, mushrooms, and onions. How in the world would you write a program to list out every single pizza you could make? You know, just pepperoni, or pepperoni and mushrooms, all 3, or just a plain cheese pizza? See, it gets complicated fast.
Well, this is where the magic really kicks in. What if I told you that a single ordinary number could represent an entire pizza order? The secret is something called a bit vector. Just think of it like a row of light switches. Each switch is for one topping. If the switch is on, that's a 1, you get the topping. If it's off, a 0, you don't. That's it. It's really that simple. Let's actually see this in action. Let's say pepperoni is the first switch, onions is the second, and mushrooms is the third, okay? Now, take the number 5. In binary, the number 5 is written as 101. So, switch 1 is on, that's pepperoni. Switch 2 is off, no onions for us, and switch 3 is on. We get mushrooms. And just like that, poof, the number 5 has magically become a pepperoni and mushroom pizza.
And this right here, this is the incantation that makes it all happen. This little loop, whether you're writing in C++ or Java, is just unbelievably powerful. All it does is count up through every number, and for each number, it just checks which bits are flipped to on to build that combination. It's a super simple, really elegant spell that just lets you try everything.
Now, why does this matter? Well, this isn't just some party trick for ordering pizza, right? This is a core technique for solving really complex problems. Anytime you're faced with a challenge and think, I need to check all possible combinations, this spell is your secret weapon. It's a huge deal in coding competitions and technical interviews. You've just learned your first truly powerful piece of programming magic.
Excellent work, apprentice. Seriously, you've just mastered a basic but super important spell. So now, let's use that knowledge to build something even bigger. We're about to construct a magical data structure that lets us do math at, and I mean this, unbelievable speeds.
Just imagine this for a second. You've got a giant scoreboard with like millions of players, and their scores are changing all the time. How could you possibly figure out the total score of the top 10,000 players instantly? I mean, adding them up one by one would take forever. We need a faster way. We need a little magic. And that magic is technically called a Fenwick Tree, but that sounds kind of boring. Let's call it the magic counting ladder. It's a really clever way to store sums of different ranges. See, instead of adding numbers one by one, each rung on this ladder holds a pre-calculated total for a whole group of players below it. By just jumping up a few rungs, we can get our answer in a handful of steps. And the secret to knowing which rung to jump to, it's all in the bits.
Okay, so what happens if a player's score changes? How do we update our magic ladder? We use what I call the climb spell. We start at the player's position, we add their new points to that rung. Then, and this is the cool part, we use this little bitwise trick, I plus I and minus I, to find the next rung we need to jump to. It looks weird, I know, but that little incantation magically tells us the next group total that needs to be updated. You just repeat that, jumping up the ladder until you reach the very top. And this is why we bother with all this magic. The speed, it is absolutely insane. Instead of taking 1,000,000 steps for 1,000,000 players, this thing takes about 20. That's what we call logarithmic time, or O of log n. It means that even if the list of players doubles in size, it only takes one extra step to get the answer. This is the difference between a program that grinds to a halt and one that feels completely instantaneous.
All right, for our final act, we're going to move away from just numbers and get a little more visual. We're going to use our bit spells to actually manipulate images, to create illusions, and yeah, even to hide secrets right out in the open.
So take a look at these two images. On the left, you've got a regular photo. On the right, a simple black and white shape. Now remember, an image is really just a giant grid of numbers, right? Each number is a pixel's color. So, what spell do you think we could use to apply the shape from image B onto image A, almost like a perfect cookie cutter?
The answer is the Bitwise AND operator. It's a masking spell. It's so cool. Just think about it. In the computer's mind, black is just a bunch of zeros, and white is a bunch of ones. So when you AND the two images together, any pixel that gets ANDed with black turns black, but any pixel ANDed with white, it stays exactly the same. It's a beautifully simple and frankly super powerful way to combine images.
Now let's try a different spell, XOR. The XOR spell is basically a difference detector. If two pixels in the exact same spot are identical, the result is black. Nothing to see here. But if they're different in any way, even slightly, the result is a bright, visible color. This is actually the magic behind motion detection in security cameras. They're just XORing one video frame with the next one to see what's changed.
And now for the grand finale. What if we could hide a secret message inside a picture and nobody could ever tell it was there? This is a real thing. It's called Steganography, and it is the ultimate bit manipulation illusion. The secret isn't in the big, obvious parts of a pixel's color, but in the tiniest, most insignificant part.
Take a look at this. You know a pixel's color is made up of red, green, and blue values? Let's just say the blue value for one pixel is 250. In binary, that number is 11111010. Now, I want you to focus all your attention on that very last digit, that lonely little zero sitting on the end. That little guy is called the least significant bit, or LSB. It has the tiniest possible effect on the overall color. So if we changed it from a 0 to a 1, the blue value would become 251. So I ask you, could your eye ever tell the difference between a blue of 250 and a blue of 251? Absolutely not. No way. But by changing that one tiny invisible bit, we can store one bit of our secret message. You do that over thousands of pixels, and you can hide an entire novel inside a single image.
And there you have it. In just a few minutes, we've gone all the way from simple pizza combinations to high-speed data structures and right into the world of visual illusions. You can see now, right? Zeros and ones aren't just boring numbers. They are literally the building blocks of magic. And I really want you to remember this. If any of this felt confusing or a little overwhelming, that is completely 100% normal. Every great programmer on this planet was once a beginner, feeling just as lost as you might feel right now. The key is not being a genius. It's about taking that feeling of confusion and patiently turning it into clarity, one little spell at a time.
And to help you on that journey, here is a little cheat sheet for your own spellbook. These are some of the most common and useful Bitwise incantations you'll come across. Think of them as your fundamental tools. You're going to use these to build even greater magic in the future.
So today, we learned to use bits to combine, to count,
and to create. We've really only just scratched the surface of this incredible hidden world. But what if we could take this even further? What if we could use these same simple zeros and ones to build entire virtual worlds, to simulate physics, maybe even to create intelligent life? Well, join me next time because we're going to explore exactly that. Keep practicing.